In this video, we're going to do something a fair bit more complicated, which is to solve the two-sum problem. We saw a variation of this already in an earlier video where we talked about the sorted two-sum problem. And the idea behind the sorted two-sum problem is that we were given an input that was an array of sorted integers, and we wanted to find two values that summed up to reach a target value and return their indexes back as a result. In this, we're basically doing the generalized version of this. In this case, the input is an array of values. It's not necessarily sorted. It could be unsorted. And a target to sum to. And the output that we're looking for, once again, is the index of the two values that sum to the target. And like our previous iteration of two-sum, we're going to assume that there's always two values that sum up to our target. And again, I'm going to assume that in this case, the list that I'm given isn't necessarily going to be sorted. The reason why this one's a little bit more tricky is because we have to be a bit more creative about the way that we're thinking about our approach. So I'm going to start out by creating my function. I'm going to talk to you a little bit about the way that we could approach this, right? So think about if you had an array of values that you wanted to try this with, say 1, 2, 2, and 7. And suppose that your target value is 9. You need to find two values that sum to reach the value 9. In order to do this, we're going to do something a little bit different, and it may seem a little odd at first, but it will make sense once we've gone through the whole approach, right? So the idea is that rather than finding two numbers that sum to reach 9, what we're going to do is on each iteration, we're going to take a look at the number that we're currently at, and we're going to ask what value needs to add to this value to reach our target. We're then going to check to see if that value exists inside of the list. And if it doesn't, then we move on to the next value. So basically for 1, we would say the value that we need to reach 9 would be, 9 minus 1 would be 8, right? So we need the value 8. So we could check to see, does 8 exist in this list? No. So then we move on to 2 and we ask, what do we need to make 2 sum to 9? Well, 9 minus 2 would be 7, right? So we would need 7 as a result. And we could look through the list and say, oh, 7 does exist. So this element here, 2, and this element here, 7, would add to our target value, right? So that's generally the approach that we're going to take. Now, with this approach, you can see pretty clearly that what we're really doing is we're saying, does a value exist inside of a list? And this is where we start to think, ooh, a hash table could be a great way to do that. So let's take that approach and see where that goes for us. I'm going to create a hash table, and it will be a dictionary, right? And I can keep track of the pair in an array here, okay? I'm going to set I equal to 0, since we'll be iterating through our list of values, and we'll have a found pair which is equal to false, just to check to see if we found what we're looking for yet. We're going to iterate our list of values twice. The first time is to track all of the values that exist inside of that array. So I'm just going to store in hash tables at num of I the index of that value. I'm going to increment I by 1. So what I'm doing here is I'm tracking the values that exist inside of the table mapped to where they exist in the table. This is an example of when we would use both values in the hash table. In this case, the key is the value, and then this is the location of that value inside of the actual list itself, right? So this gets us all of the values that are inside of our array. From here, I can iterate again, and I could say, okay, well, the length of numbers, well, I is less than the length of numbers, and we haven't found our pair. What we're going to do is we're going to calculate the complement, I'll call it. And this is the value that we need to find in order to sum up to our target. So the way that we find that is we just do target minus nums at I, right? That would tell us what number we need to find in order to sum up to our target. And then what we do is we just simply check if that value is in our hash table. If it is inside of the hash table, we need to check one more thing. And that's just that the value isn't the current value that we're at. The reason for this is basically like if you had a target, say, of 4 and your current value is 2, technically adding 2 to itself would get us to 4. However, we're asking for two distinctive numbers. So we want to make sure that we don't return back the same number twice. That's what this if statement is doing. So if it's not the same number twice, then we just go ahead and append to our pair the values I, and we can append to our pair the hash table of complement. And actually, as I'm thinking about this, really the better way to do this would be to say pair equals I, and then we would put in the hash table complement, right? This probably makes more sense as the actual result here, right? So we could say something like this, and then we could say found pair equals true. That way we exit out of the loop. And if all of that doesn't happen, then we just simply increment I by 1 and we move on to the next value inside of our iteration. And then at the end of this, we're just going to go ahead and return back the pair. So let's just give this a try with our actual example. So the example that I had was 1, 2, 2, 7, and the target I was trying to reach was 9. Let's take a look and see if we actually get that value or not. So I'm going to do chapter 6, tosum.py. You can see I get the value 1 and 3. So you see here index 1 and index 3. That's exactly what we were expecting as a result. So you can see that this does look to work pretty well for our tosum problem. And now it works great, even if the list isn't sorted. In this case, it happens to be sorted, but, we could have just as easily flipped these around. And if we were to do that, we would now get 0 and 2. So this one here and this one here, right? So you see that we get essentially the same sort of answer, even if we flip the values around, even if they're not sorted, right? So when we look at this, we can consider the time complexity as well, which is important. This function here is O of n. It iterates the whole array at least once, right? Again, I'm sort of assuming that these hash table functions are constant time. You'll generally see that as a convention, that most people will assume that these are constant time-based operations. So then this iteration also is going to run O of n times. So when we look inside of here, we see a few different hash table operations. Again, we'll assume that they're mostly constant time. This subtraction is constant time, so really we're just going through the array twice, right? So in this case, we do have a linear time complexity. So it's going to be generally O of n, technically O of 2n because we have to iterate the list twice, but generally it's linear time complexity, right? So that's all we really care about in this case. So you can see how sometimes we have to use the hash table in a bit more of a creative way, right? In this situation, we had to do a little bit of a stretch to get the hash table to fit the problem, but once we did, we got a pretty good time complexity out of the actual problem approach that we took itself. So this is another example of how we can use a hash table to be able to look for values that we've seen inside of an array and use that information in order to help us with solving our problem. So thanks so much for watching this video, and I'll see you in the next one.